Nuclear fusion as presented by Olivia Wolliver. Let's look at the nuclear chemistry involved with nuclear fusion. The substance that we use for this is uranium. Uranium has primarily two isotopes, uranium-238 and uranium-235. The most common is uranium U-238. U-238 is more stable, and therefore when it's bombarded with neutrons, they are absorbed, or uranium-238 requires very high energy neutrons for a reaction to occur. Uranium-235, on the other hand, is less stable, and therefore when it's bombarded with low energy neutrons, its nucleus splits. When the nuclei split, this emits extra neutrons, allowing the initial fission to generate a chain reaction. So how do we separate the two isotopes? The isotopes are almost identical aside from their weight. There is no way to separate the isotopes without manipulating their weight. U-235 is slightly lighter, and therefore it travels faster when put into a tube inside a chamber that is under pressure. There is a pressure difference between the tube and the chamber, so therefore more U-235, which is this enriched stream, passes through the chamber, and more U-238 gets stuck within the tube. To increase the separation, the slightly enriched stream goes through many more stages just like this. It goes through approximately 4,000 stages. There's also another way to separate the isotopes. Again, there's no way to separate the isotopes without manipulating their weight. Another way to do this is by using a centrifuge, where the outside cylinder is stable and the inside cylinder rotates. During this centrifuge spinning, the U-238 moves towards the outer walls of the cylinder, while the U-235 is moved inward. The enriched stream is then removed and sent through another centrifuge. This would need to happen throughout about 60,000 centrifuges to get an enriched stream that we would need. In conclusion, in order to create nuclear fusion, we need to use uranium isotope U-235. U-235 is unstable and sets off a chain reaction when bombarded with low-energy neutrons. In order to separate the isotopes, we must manipulate them by their weight. We can do this by acres of pressure tubes and chambers, or by thousands and thousands of centrifuges, both of which have their shortcomings. The pressure tubes and chambers require an extreme amount of energy to function and are costly when building acres worth of these mazes. The centrifuges only require 4% of the energy of the tubes and chambers, but the precision necessary to build the centrifuges makes it an incredible feat to have 60,000 functioning properly. We consider these shortcomings a good thing to reduce the likelihood of nuclear fusion events occurring.